Final talk of this week of the conference. Remember that next week we'll have a workshop with 3 mini courses. The next week lectures will be not in this audience but next door. In audience number 1. It's smaller, but I think we will all fit. So for those who are staying, see you next week. And our next speaker is Jessica Purcell from Monash University in Australia. I came prepared. She will talk about drilling and filling tame hyperbolic 3 manifolds. Thank you.
Okay, thank you. Can you hear me? Is my microphone on? Okay, great, good. Since this is the last talk of the conference, I think we should take a minute to thank the organizers of what has been a really great week with some really excellent talks. So thank you, organizers. The talks have been excellent. The food has been excellent. If you could do something about the mosquitoes, I would appreciate it. All right. Thanks very much again. thanks very much for inviting me. This is all joint work with David Feuder and Saul Schleimer. It's some work that we did a couple of years ago, so you can find it on the archive if you want to follow along and or look up some details that I brush over. So I think someone said we're supposed to start with the theorem of Thurston. All right, so let's talk a little about hyperbolic geometry of Dehn fillings. Okay, so that's where this project kind of arose, is a desire to understand geometry change under Dehn filling. And this really goes back to work of Thurston, in particular his hyperbolic Dehn surgery theorem. So what he said is that, his theorem is that if M, well, let me maybe move over here. So let's say that M is hyperbolic, and it has a torus boundary component. Then this boundary inherits a Euclidean metric. By chopping off a horosphere, for example, and then a slope S on dm has a length. And the theorem states that as this length goes to infinity, the Dehn filling well, let's give this Sn. So the Dehn filling M of Sn approaches M in the geometric topology. So as a geometric limit, in other words. Okay, so we've been here a whole week, and so now we all know all of the words associated with all of geometry because it happened in somebody else's talk, right? But I'm not going to be able to assume everybody else's talks because I was quite jet lagged the first 2 days, and I missed most of those. I was here, but not here. So I'm going to review a lot of the terms that are here in this theorem to get started, and then kind of explain why this is a great theorem and why this is not quite good enough theorem. Some of the things that we would like to have beyond what's here. Yeah, let me describe that. Let me start actually with, let's describe a Dane filling and all of the things that are involved with that, including a slope. Okay? So I think this is bad chalk. Let me switch. Okay. So the Dane filling, everything here is going to be three-dimensional. So if M is a compact three-manifold with a torus boundary component, then a slope S is an isotopy class of simple closed curves on the torus. Okay, so the fundamental group of the torus is Z2. A slope is just some PQ, relatively prime, that are determining this isotopy class of simple closed curves. And so under the metric, on this Euclidean metric, you can take a geodesic representative of that, and it's going to have a well-defined minimal length. That's how you define the length of a slope. Okay, so what do you do with this slope? Well, this slope is living on this torus. We're going to modify M by attaching a solid torus. Okay. And along the common boundary. Such that this slope S, our chosen one, is bounding a D2 in the result. Okay, so cartoon of what's happening. Here's our manifold. We have some sort of a curve. Okay, so here's an S. And then we're going to glue on this solid torus and S now. Right, so this disk gets attached to S. So this is a Dane filling. So we've seen this in some other contexts. In terms of group theory, it adds a relation. But topologically, this is all that's happening here. Okay, and if M has multiple torus boundary components, then you can Dane fill all of them, and we will. So our goal is to relate the hyperbolic geometry of a Dane filling to the hyperbolic geometry of the original manifold. Okay? And this is what Thurston's theorem does. It says that these Dane fillings approach the hyperbolic structure on M in the geometric topology. All right, so this is a very important theorem, Thurston's theorem. It says that, so most three manifolds are hyperbolic. So this is often how we state the theorem is, but what it is missing is something that is effective. Okay, so how long? So, okay, most three manifolds are hyperbolic. What this means is for long enough, Sn means that M of Sn is hyperbolic. But how long is long enough? Okay, And we're approaching the limit in the geometric topology. I'll say a little bit more about what that is. That has some consequences for geometry. So you can relate geometric properties of one manifold to geometric properties of the other. But again, how far do you have to go? How sharp? What are the bounds? How do you pick some of those up? And you can't really get those from Thurston's theorem as it is stated. So we need a little bit more work. Okay, so yeah, so maybe let me just write that here. So geometric convergence. So various geometric properties converge, but how fast? What are the parameters on that? Okay, so this is the type of theorem. Thurston's theorem is a great theorem if you're looking at limiting behavior. But if you have an example in mind and you want to say something about that, it doesn't do enough for you. Okay, so a little bit of history then. This Thurston's theorem is in his 1979 notes. Since then, there has been significant progress over the years trying to improve the theorem into something that's a little bit more usable for examples. So for example, so if you're looking at hyperbolicity only, right, so how long is long enough to be hyperbolic? So this was answered a few different ways. So there's the Gromov-Thurston 2-pi theorem. Was the first result along these lines that says that if you have a slope of length at least 2 pi, there's a negatively curved metric on the Dane filling, which then by the geometrization theorem 2002, 2003, that will then be hyperbolic. Okay, so this one was, a proof of this was given by Bleiler-Hodgson, I think in the 1980s, 1990s. There's also the sixth theorem due to Agel and Lackenby that sharpened this, both in 2000. This is a comma. They did it independently. The sixth theorem says that if your slope length is at least 6, then your manifold is what they called hyperbolike. Again, with the resolution of the geometrization theorem just a few years later, this implies that that's a hyperbolic manifold. And then for geometric control, the best results really have been due to Hodgson-Kirchhoff, still probably, using cone deformation techniques. So they have a 7.515 theorem that says that if the normalized length of the slope, so the length divided by the square root of area, we'll come back to that, if the normalized length is at least 7.515, then not only will the result be hyperbolic, but you can actually deform it through incomplete, indiscrete groups, incomplete metrics from cone angle 0 down to cone angle pi, so the cusp manifold to the filled manifold. And if you work through some of the analysis here, you can hang on to a lot of the geometry change along the way. Okay, so this is our next, the next step along the way that we want. Okay, so let me just say something very quickly about cone deformation. So if you have a hyperbolic manifold, which is the interior of a compact manifold with torus boundary, so okay, I'm a little bit sloppy. So if M is hyperbolic, then technically it's the interior of a compact manifold with torus boundary. It doesn't have a torus boundary component. But the Dane filling requires the boundary component. So anyway, so cut along horospheres when necessary, or take the compactification when necessary. Okay. But all right, so in our setting, if M is hyperbolic, with a cusp, with this torus, this is a cusp torus. So it's modeled by the quotient of a Horobal, quotiented out by a Z cross Z subgroup. Okay, that's going to give you your manifold with torus boundary. So what is a cone manifold? It's locally modeled on hyperbolic space. So every point has a neighborhood that's isometric to hyperbolic space, except there's going to be a singular locus. And at points along the singular locus, this is going to be a closed geodesic in our case. Closed, or a union of closed geodesics. And a neighborhood of a point on the singular locus will be a bit of a neighborhood of a tube, where this disk here has some sort of a cone of angle alpha. Okay, so if alpha is less than 2 pi, then your cone will look, your neighborhood of the point will look like this product with an open interval. And if your cone angle is 2 pi, then your cone manifold actually has a smooth structure. So this is non-singular. Complete hyperbolic structure. Okay, so the cusp is actually cone angle 0. And so in order to do the cone deformation, what you can do is you can write points around the singular locus. You can put them into cylindrical coordinates. You can describe what the metric is going to look like, how the metric is changing. And what Hodgson and Kirchhoff did is they gave some conditions that would ensure that you could start with cone angle 0, and you could deform all the way to cone angle 2 pi. And when you get here, technically what you really have is an incomplete structure, but the completion now is going to be smooth. Okay? Okay, so again, the point is at cone angle at 0. Cone angle 0, we've got the cusp. At cone angle 2 pi, we have the complete hyperbolic structure with geodesics. And we're going to be interpolating between them. Okay, so our hope is, again, we're trying to make Thurston's surgery theorem effective. And the first, well, a next variation on this is due to Brock and Bromberg, the drilling theorem. Let me write that down. Okay, so this theorem has more to say about geometry changing. So pick your favorite constants, j greater than 1, epsilon greater than 0. make sure that epsilon is less than universal Margulis constant for hyperbolic 3 manifolds. Then there is some L naught, which depends only on your choice of epsilon and j. It's independent of your manifold. Okay, such that for any geometrically finite hyperbolic 3 manifold Y without rank 1 cusps, if you have sigma a geodesic, so sigma is going to be your cone locus, and it has length, total length less than L naught, then y minus sigma admits a hyperbolic structure with the same end invariance and the inclusion is a J by Lipschitz diffeomorphism on the epsilon, or on a complement of epsilon tubes. All right, this I wrote too big. Okay, so let me take a second to digest that. All right, so the drilling theorem. So what it says is the big new thing is you get a J by Lipschitz diffeomorphism of your drilled manifold and your filled manifold, and you get to pick J. The diffeomorphism isn't going to go all the way into a neighborhood of the tube. It shouldn't. You've changed your topology there, so you're certainly changing your geometry. But you can pick how far you go. So pick your favorite J, pick your favorite epsilon. If you need the geometry to be yay precise, you can do that. Their theorem tells you there is some length such that if you have appropriate hypotheses, then you get a hyperbolic structure. You get a J by Lipschitz diffeomorphism from your drilled manifold to, or let's see, this is the, actually it can go both ways. From Z to, Z is the drilled manifold to the filled manifold. Okay? Okay, so with Dave and Saul, we needed this for an application, but it still is not quite strong enough because of this little symbol right here. So there exists some L naught, but how do you find it? And there were lots and lots of hints in this paper as to how one might find it, but it wasn't effective. And so we had to do a little bit more work. So, okay, so can we find it? So, so yes, kind of. Okay, so what we were able to show is, again, if you fix epsilon fix an epsilon, fix a J, you have N is a hyperbolic three-manifold. Sigma, a geodesic length. Okay, and then you have a drilling version. Okay, sorry, so N is just a three-manifold to begin with. In the drilling version, N is hyperbolic. The length of sigma is less than some explicit function, but messy. So I'm going to suppress it. I don't think it's insightful for purposes of the talk, but you can look it up. It's explicit. Or filling N minus sigma is hyperbolic with normalized lengths of these. So the normalized length is length over the square root of the area. So if the sum of the normalized lengths are big, so again, an explicit bound, then what do you get? Then you get the drilled or filled manifold is also hyperbolic, and you get inclusions, J by Lipschitz inclusions. In both directions. Okay, and I need the first version of this, N is finite volume. Okay. So, all right, so this is kind of a lot of words, but basically, starting with a hyperbolic three-manifold and a geodesic length inside of it, finite volume, provided the lengths of your curves are small enough. I think Ursula mentioned this. If the lengths are small enough, you can drill them. Actually, if you have a geodesic link, you can drill them anyway, and you'll get something hyperbolic. But if they're a short enough length, then you can deform via cone deformation, and you can follow the geometry along the way. And as you follow them through, you're going to get J by Lipschitz inclusions on the thick parts. So this is not quite as it's not as good as this theorem in a few different ways, but it does have the effective bounds that we were looking for. So one way that we're failing is we can't go into thin parts away from tubes, but they can. And then everything is finite volume. So that's a bit of a problem too. Or it's a difference. Okay? So any questions so far? All right, so we're going to upgrade that. So this is not quite what I want to talk about today, but we're getting closer. It's a good thing because we're halfway through. Okay, so today what we're going to do is we're going to extend to infinite volume hyperbolic three manifolds, so tame manifolds. And we are going to do it in such a way that no cone deformations will be required beyond what has already happened over here. Okay. Okay, so before I state the theorem, I mean, it's essentially this theorem, only now we allow n is a tame three-manifold. But before I state it, maybe let me review some of the anatomy of tame three-manifolds. So a hyperbolic three-manifold Okay, so if it's the interior of a compact three-manifold with boundary, and by the tameness theorem, due to Agel and Caligari goodbye, if n is hyperbolic with finitely generated fundamental group, then n is tame. So n is the interior of some compact three-manifold. Okay, so then I can draw some of the pictures that are similar to what many of you have been drawing. So here's some sort of a compact three-manifold with boundary. It's going to have some topology in here. But the important part of these manifolds for purposes of classification and geometry are these boundary components, are the ends. Okay, so we are going to allow all sorts of cusps, rank 1 and rank 2, for our manifolds. And so in order to do this, we're going to paint some portion of the boundary of n. So any torus. All right, let me see how I want to say this. So paint so we're going to paint them green, because here's green. You can't see that this is green, but it is. And then what we're going to do is you can also choose a collection of essential annuli on the boundary of n, and you can paint that green. Choose essential annuli. And dn is what I'm calling it. And all of these green surfaces get placed into what we call the P, which is the pairing locus. Okay, so then we obtain what is called a paired manifold. And here, this is going to be a paired manifold if a few conditions. So we don't allow a 3-ball or a solid torus. And every pi1 injective map of a torus is homotopic into P, and pi1 injective map of an annulus with boundary components in P is also homotopic into P. Okay, these are conditions that you need basically to ensure that there is a hyperbolic structure on this thing. With your chosen P is going to be parabolic. Okay, so we're going to say that the remaining boundary components are the ends of n bar. And if it happens that we have nothing left, then we only had torus boundary components, then this was a finite volume manifold. Okay, so finite volume manifolds work just fine in this setting. We need to worry about geometrically finite, which I'm going to denote as GFMP. So if you have a geometrically finite hyperbolic structure, let's see. Then there's some sort of a finite-sided convex set in hyperbolic 3 space such that phase pairings will give you, well, n. Okay, so this is going to be our definition. So for example, your classical Schottky group gives you a geometrically finite structure. If you take the complement of two half planes and you glue those together, this is a finite-sided. It's got these two planes I'm counting as sides, and it's convex. And when we glue this guy to this guy, we're going to get a, in this case, a solid torus, which I actually don't want. So let's put in a couple more. Okay, so there's a genus 2 handle body. All right, and what if I had some bit of parabolic locus? So what if, for example, this curve here was part of my annulus? Well, that's fine. You just can, you can ensure that there's a fixed point here of your gluing. Okay, so you can make this, you can arrange this to work. Okay, so geometrically finite structures. So just if we have a phase pairing of a convex fundamental domain. So it follows from the Alfors-Behr's uniformization theorem, due to work of many people, that the geometrically finite, I should say minimally parabolic. So I'm requiring P to stay parabolic throughout, but minimally parabolic geometrically finite structures are uniquely determined by conformal structure on the boundary. All right, so if we have an incompressible boundary then the geometrically finite structure is equal to the product of the Teichmüller space. So okay, and if it's compressible, then we have a this is a covering map. Okay, so this is well understood, what happens in the geometrically finite case. I'm heading towards this because we're going to need to know what's happening on the ends of our three-manifold. And so the third situation that can happen is that you can have a degenerate end. Okay, so roughly, without going through technical details, these historically they arose as limits of geometrically finite structures. So one way that you can build these is that you add more and more faces to your geometrically finite convex region, for example, as you deform things. And in the limit, this developing image of this identification is going to swallow up all of the conformal boundary, basically. So all right, let me just state, okay, let's if you have a one-ended hyperbolic three-manifold, then it's uniquely determined by its ending lamination. And let me just state this rather than define this, I'm just going to say this is this is how you determine this thing. A geometrically infinite manifold okay, and then more generally, if you have multiple ends, so you'll have, say, some F1 through Fn, then some of them may be geometrically, let's go up to Fk. Some of them may be geometrically finite. Some of them may be geometrically infinite. And the hyperbolic structure on n is uniquely determined by the conformal structure of the geometrically finite ends and the ending lamination of the others. Okay, so this is a major theorem in hyperbolic geometry. Many of you will know it better than I do. But this gives us the setup for the restatement of our theorem. So we wanted to extend this to tame, and I did my board work poorly. I've just erased the theorem. But basically, what you get so again, you pick your epsilon, you pick your j, and you let y be a tame hyperbolic 3-manifold, sigma a geodesic link, with a length that's bounded by some function of epsilon and j. Okay. Okay, so then you have your drilled manifold has a hyperbolic structure with exactly the same end invariance, and there are j by Lipschitz inclusions from the thick part, the epsilon thick part of y to the, sorry, let's call that z. The epsilon over 1.2 thick part of z and the other way around. Okay, so this is very good. This is strong geometric control. So this improves Brock-Bromberg in a couple of ways and doesn't quite get as far as they do in another way. So in particular, we have no restrictions on cusps. We have no restrictions on geometrically finite manifolds. So this will work for your favorite hyperbolic 3-manifold that is tame, whatever it is. It's effective. So you can plug it into your computer, and you will know the geometric bounds. But again, we only get results in the thick part, whereas they were able to just avoid tubes around the singular locus. So we have to avoid other thin parts of the manifold. Okay, so I reviewed all of this, what is now important hyperbolic geometry, because the proof of this theorem is kind of a who's who in major theorems in hyperbolic geometry. So if you're happy with the statements of these theorems, then it won't take us very long to go through the proof. So that's my plan for the next, I don't know. There's nobody speaking until 5:30. Okay. Okay, there were 3 major theorems in Kleinian groups proved in the 2000s, I would say. The ending lamination theorem, the tameness theorem, and I've missed one. Which one? Density theorem. And I'm going to use the strong density theorem that is due, the formulation is due to Namazi-Soto, which says that if you have a finitely generated, we're going to stick with torsion-free. We're interested in manifolds, but there's probably an orbifold version of this. So torsion-free Kleinian group, there's a paired manifold. So this is if and only if, sorry, so and rho is the inclusion. Then the result is there exists a sequence of representations, rho n, converging strongly to rho. Okay, so this is the careful statement of it. For purposes of this talk, what we have, we get these geometrically finite hyperbolic structures on the same paired manifold that we started with. And the fact that they converge strongly, this means that they converge in the algebraic and the geometric topology. We care most about the geometric topology, which you can take to be the following, so strong. So there exists geometrically finite hyperbolic structures on the paired manifold. So I should say minimally parabolic as well. Such that you need a base point for each of them. I'm trying to do this in a minimal amount of words. So this geometric convergence means you get, let's put it this way, so better and better. Almost isometric convergence on larger and larger balls. At base points. Okay, so you've got a sequence of geometrically finite manifolds. They're not geometrically infinite, but you have balls in the geometrically finite ones that map into the geometrically infinite one, or vice versa. And you have your map is almost an isometry, and the constant of almost isometry gets better and better, and your balls get bigger and bigger. Okay. Okay, so step one of our proof is we have a hyperbolic 3 manifold. We're going to approximate it by geometrically finite hyperbolic structures converging to this in the geometric limit. Okay. Okay, older work of Brooks. So this is from the 1980s. He showed that for any geometrically finite hyperbolic 3 manifold, you can approximate geometrically finite by circle pact. So what is that? So on the conformal boundary, you can cover the conformal boundary with a collection of disks meeting in interstitial, or in triangle, yeah. Okay, so what does this mean? So you've got this conformal boundary somewhere. you just start drawing disks that are disjoint, and you make sure that they intersect in triples so that you have these interstitial triangles between them. And if you take your favorite geometrically finite structure, you can do this. You can just keep packing things in. But what Brooks found is that eventually you may get a quad. And then you can pack stuff into a quad, but you'll get another quad. And then another quad, and another quad, and another quad. These quads are getting smaller and smaller. If you are as small as you want, you just bump things a tiny bit, so deform the structure slightly. And it closes up to a triangle, and you have a circle packing. OK, so we're going to do that on all of our geometrically finite things. So step 2 is we now take Cn. These are circle packed, converging to our Yn, converging to y. OK, and this is basically the way the proof goes. So, which is good, because you don't really want to stay until 5:30. OK, so this is the proof of the drilling theorem. Here's our manifold that we want to drill. It has this geodesic link sigma inside of it. We approximate it. OK, so using one major theorem with the density theorem. And then we approximate it using another major theorem from Brooks. Circle packed. So these circles all live on the conformal boundary. So they're just Euclidean circles on the Riemann sphere when you lift to the universal cover. Yeah. OK. Yeah, but then what you're going to do with these circle packed things is you're going to scoop. So what do I mean by that? So you've got these circles living on your conformal boundary. These circles determine half planes, which determine half spaces, which you throw away. And once you have thrown away all of these, you have these triangular regions, which you put a circle around. And then you throw that away. So after you throw away all of these half spaces and all of the triangular half spaces, what you have is a manifold that looks like it's like a crampon, right? It's spikes. You have this is the scooped manifold. So you remove half spaces bounded by circles and these triangular interstitial regions. And this is a 3-manifold with corners. And lots of spikes. But what this is infinite volume, or sorry, this is finite volume now. You've taken away all of the infinite part. OK? Double. So if you double along the circles and then you double along the triangles, this is now finite volume, smooth hyperbolic 3-manifold with billions of rank 2 cusps. This sigma is in every single one of these as long as you're approximating close enough. That looks like an M, huh? You're supposed to look at it sideways. It's a sigma. So I can drill. And then my finite volume drilling theorem implies that there are J by Lipschitz diffeomorphisms. OK, now go backwards. So this embeds isometrically into a scooped manifold which embeds isometrically into this circle-packed manifold, which approaches in a geometric limit a geometrically finite manifold, which approaches this hyperbolic manifold, y minus sigma. And then you just check all along the way, the end invariants here agree with the end invariants here. Okay, so by convergence, you're going to get your J-Lifshitz diffeomorphism that goes like this. And because the end invariants agree, the ending lamination theorem implies that this is the map that we want. Okay, the end. Thank you.